For most of human history, the universe felt like a distant backdrop. The stars were beautiful but unreachable, and the deepest questions about where everything came from seemed permanently out of reach. Even after the invention of telescopes, our understanding of the universe grew slowly, piece by piece, limited by what our instruments could detect. Every new telescope sharpened the picture a little more, but the basic outline stayed the same. The universe had a beginning. It expanded. Galaxies formed gradually. Stars were born, lived, and died, and the story unfolded at a pace that seemed well understood. Then the James Webb Space Telescope began sending back data. Almost immediately, astronomers realized something was off. Not broken, not wrong in a simple sense, but fundamentally surprising. Webb was not just filling in missing details. It was showing a universe that looked older, larger, more organized, and more chemically mature at very early times than anyone had predicted. The carefully built models that explained cosmic history suddenly felt incomplete. To understand why this matters, it helps to start with what James Webb actually is, and what it is not. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep, to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Now, let's begin. James Webb is often described as the successor to the Hubble Space Telescope, but that description can be misleading. Hubble and Webb are not upgrades in the way one phone replaces another. They are designed to see the universe in very different ways. Hubble primarily observes visible and ultraviolet light, the same kind of light our eyes detect. That makes Hubble excellent for producing iconic images of galaxies, nebulae, and star-forming regions. But visible light has a problem. It struggles to travel long distances through the universe without being scattered, absorbed, or stretched beyond recognition. Webb, by contrast, is an infrared telescope. Infrared light has longer wavelengths than visible light, which gives it two enormous advantages. First, it can pass through dust that blocks visible light. Second, it can capture light that has been stretched by the expansion of the universe itself. This stretching, known as redshift, shifts light from distant objects out of the visible range and into the infrared. An easy way to think about this is sound. A high-pitched siren passing by drops in pitch as it moves away. Light behaves in a similar way as space expands. The farther the light has traveled, the more it stretches, and the lower its energy becomes. Hubble can hear only the higher pitches. Webb can hear the deep, slow notes that have traveled across billions of years. This ability allows Webb to see objects that existed when the universe was extremely young, only a few 100 million years after the Big Bang. Before Webb, astronomers believed they had a rough idea of what this early universe looked like. It was supposed to be messy, chaotic, and dim. Galaxies were expected to be small, irregular, and slowly assembling their first generations of stars. Instead, Webb found galaxies that looked unexpectedly mature. These early galaxies were bright, massive, and well-structured. Some showed signs of organized rotation. Others contained far more stars than models allowed for at such early times. It was like opening an old history book and discovering photographs of modern cities in what should have been the Stone Age. This wasn't just one strange object either. Webb kept finding them. Survey after survey revealed galaxies that challenged timelines astronomers had spent decades refining. The universe, it seemed, had wasted no time getting organized. This discovery immediately raised a deeper question. If galaxies formed this early and this efficiently, then perhaps the universe itself evolved faster than we thought. And if that's true, then our understanding of cosmic size, growth, and structure may also be incomplete. The size of the universe is already a difficult concept to grasp. The observable universe, the portion we can see because light has had time to reach us, spans about 93 billion light-years in diameter. That number alone feels absurd, but Webb complicated the picture even further. By detecting early galaxies spread across vast distances, Webb confirmed that large-scale structure emerged very quickly. Cosmic filaments, clusters, and voids may have begun forming far earlier than expected. This matters because structure does not form randomly. It follows the invisible influence of dark matter, which acts like a scaffold that ordinary matter falls into. If structure appeared earlier, then dark matter must have been clumping efficiently very early in cosmic history. That places new constraints on what dark matter can be and how it behaves. Webb also began reshaping our understanding of time itself in cosmology. When astronomers look farther into space, they are also looking backward in time. Each photon carries a timestamp of when it was emitted. Webb's ability to capture ancient light turns the universe into a kind of time machine. But unlike a neat timeline, the universe's history now looks compressed at the beginning, a lot happening very fast. This acceleration of cosmic development raises uncomfortable but exciting questions. Were our initial conditions wrong? Did stars form faster? Did gas cool more efficiently? Did black holes grow in ways we don't yet understand? Black holes, in particular, became a major surprise. Webb detected evidence of supermassive black holes existing when the universe was extremely young. According to previous models, there simply wasn't enough time for black holes to grow that large through known processes. This suggests either that black holes formed through different mechanisms early on, or that growth was far more aggressive than expected. Imagine finding a fully grown oak tree in a field where you thought the seeds had just been planted. Either the tree grows much faster than you believed, or something else happened before you started watching. Webb's discoveries forced scientists to confront that possibility across multiple areas of cosmology. Another major shift came from Webb's ability to analyze chemical composition. Using spectroscopy, Webb can break incoming light into its component wavelengths, revealing the fingerprints of different atoms and molecules. In early galaxies, Webb detected heavier elements, carbon, oxygen, nitrogen, in higher quantities than expected. These elements form inside stars and are released when stars die. Finding them early suggests that multiple generations of stars lived and died very quickly. This chemical maturity is significant because heavy elements are essential for planets, complex chemistry, and eventually life. Webb's observations imply that the building blocks of life were present in the universe much earlier than previously thought. At the same time, Webb has been examining exoplanets, planets orbiting other stars, with unprecedented detail. It can measure atmospheric composition, temperature differences, and cloud structures. While Webb has not found life, it has shown that planets with complex atmospheres are common. This reframes the question from, "Are life-friendly worlds rare?" to, "How many are there?" All of this points to a larger realization. James Webb is not simply refining existing knowledge. It is stress-testing the foundations of modern cosmology. The standard model of cosmology still works remarkably well on large scales, but Webb's data suggests that the early universe does not behave as neatly as our equations assumed. This is not a failure of science. It is science working exactly as intended. Every major advance in astronomy has come from instruments that revealed something unexpected. Galileo's telescope showed moons around Jupiter. Hubble revealed that galaxies exist beyond the Milky Way. Webb is continuing that tradition, not by tearing down physics, but by revealing where it needs to grow. As we move deeper into Webb's discoveries, one theme becomes clear. The universe is not just bigger than we imagined. It is faster, richer, and more complex, and it has been that way from very early on. What we thought was a slow cosmic childhood now looks more like a rapid, energetic adolescence. This realization sets the stage for everything that follows. To understand how Webb reshaped our picture of the universe's size, structure, history, and contents, we first had to learn how different its vision really is, and why seeing in infrared has allowed us to glimpse a universe that was hiding in plain sight. When we talk about the size of the universe, it's tempting to imagine a giant container with edges, like a cosmic room we're slowly mapping out. But the universe doesn't work that way, and James Webb has made this fact impossible to ignore. One of Webb's biggest contributions isn't just showing us new objects, but forcing us to rethink what distance even means in an expanding universe. In everyday life, distance is simple. A mile is a mile whether you measure it today or tomorrow. Space, however, does not behave like a fixed grid. The universe expands, and that expansion stretches the distances between objects over time. This means that when we observe something extremely far away, we're seeing it as it was when the universe itself was smaller. Before Webb, astronomers estimated cosmic distances using a combination of methods: brightness comparisons, redshift measurements, and models of cosmic expansion. These tools worked well, but they relied on assumptions about how fast the universe expanded at different times, and how quickly structures like galaxies formed. Webb's observations are now testing those assumptions in a very direct way. To understand how Webb reshapes cosmic scale, it helps to think of the universe like a loaf of rising bread. The raisins inside represent galaxies. As the bread rises, the raisins move away from each other, not because they're traveling through the dough, but because the dough itself is expanding. If you were a raisin, every other raisin would appear to be moving away from you, and the farther ones would recede faster. That analogy works well, but Webb has shown us something unexpected. Some raisins were already large and well-formed very early in the baking process. That forces us to reconsider how quickly the bread rose, and how fast raisins could grow. James Webb measures distance primarily through redshift. When light travels through expanding space, its wavelength stretches. The more stretched the light, the farther it has traveled, and the earlier in cosmic history it was emitted. Webb's infrared sensitivity allows it to measure extremely high redshifts with precision, meaning it can place galaxies very accurately on the cosmic timeline. What Webb found was surprising. Some galaxies with extremely high redshifts, meaning they existed very early, were brighter and more massive than expected. Brightness matters because astronomers often estimate distance by comparing how bright something appears to how bright it should be. If early galaxies are brighter than predicted, then previous distance estimates may need adjustment. This doesn't mean everything we knew was wrong. It means our cosmic yardstick needs recalibration. Another important shift comes from Webb's ability to observe large-scale structure earlier than ever before. Galaxies are not randomly scattered. They form vast networks called cosmic filaments, with enormous voids in between. Before Webb, scientists believed these structures took a long time to emerge. Webb's data suggests that this cosmic web may have started forming much earlier. Imagine looking at a city skyline under construction. If you expect to see only scaffolding and foundations, but instead you find completed skyscrapers, you'd question your timeline. Webb is doing exactly that to cosmology. This early structure affects how we estimate the universe's overall size. The observable universe is defined by how far light has had time to travel since the Big Bang. But if structure formed earlier and light sources were brighter sooner, then our observational horizon may be richer and more complex than we assumed. Webb also refines measurements of cosmic expansion itself. One of the biggest debates in modern cosmology is the Hubble tension, a disagreement between different methods of measuring how fast the universe is expanding. Webb contributes by improving measurements of distant galaxies and stars used as cosmic distance markers. By observing variable stars and supernovae in infrared, Webb reduces errors caused by dust and gas. This leads to more accurate distance measurements and sharper estimates of expansion rates. Early results suggest that the tension is real, not a measurement mistake. That implies something fundamental about the universe's expansion may be missing from our models. In simple terms, the universe might not be expanding the same way everywhere or at every time. That possibility opens the door to new physics. Another way Webb changes our perception of size is by revealing how much empty space actually contains. Infrared observations show faint galaxies and star-forming regions that were previously invisible. What once looked like darkness is now populated with structure. The universe feels larger not just because it extends farther, but because it's more filled than we thought. This leads to an important psychological shift. The universe isn't a sparse place with isolated islands of matter. It's a dense, interconnected system where even the darkest regions often hide activity. Webb's precision also helps clarify the difference between physical distance and observational distance. Some galaxies Webb sees are now much farther away than where they appear to be, because space has continued expanding since their light was emitted. This creates a universe where objects can be both near in time and extremely far in space, depending on how you define distance. It's like seeing a photograph of someone taken years ago. The image feels close and immediate, but the person has moved on. Webb is giving us a universe full of very old photographs, snapshots of places that have since drifted far beyond their original positions. All of this reshapes how we think about the scale of existence. The universe is not just vast, it is dynamic. Distances stretch, structures evolve, and size itself depends on when and how you measure it. James Webb doesn't simplify this picture. It makes it more honest. By sharpening our measurements and revealing unexpected early complexity, Webb shows us that the universe reached maturity faster than expected. That realization forces us to rethink timelines, distances, and the true scope of cosmic history. And this is just the beginning. Understanding size naturally leads to a deeper question. If the universe grew so quickly and became so complex so early, how did it start that way in the first place? To answer that, we need to look even farther back in time. And that's where Webb's insights into cosmic history truly begin to challenge our assumptions. When James Webb looks deep into space, it is also looking far back in time. Because light takes time to travel, the most distant objects we see are also the oldest. Before Webb, astronomers believed they had a reasonably good outline of how the early universe unfolded. The broad story went like this. After the Big Bang, the universe cooled. Simple atoms formed. Darkness followed for hundreds of millions of years, and then the first stars slowly ignited, assembling into small, faint galaxies that gradually grew larger over billions of years. Webb has not thrown this story away, but it has added chapters far earlier than expected, and those chapters are surprisingly detailed. One of Webb's most important discoveries is that galaxies appeared earlier and matured faster than existing models predicted. Some galaxies observed by Webb existed only a few 100 million years after the Big Bang, yet they already show clear structure, large stellar populations, and significant mass. This is like finding fully grown trees in what should still be a freshly planted forest. To understand why this matters, imagine trying to explain how a city formed. If you expect to see small huts first and skyscrapers much later, discovering high-rise buildings in the earliest photographs would force you to rethink construction speed, resource availability, and planning rules. Webb is showing cosmologists a universe that built complexity very quickly. Galaxies form when gravity pulls gas together, triggering star formation. Stars then produce heavier elements, which help cool gas and accelerate further growth. This feedback loop takes time. Before Webb, scientists assumed this process was slow at first because the early universe lacked heavy elements. Webb's observations suggest either that the process was more efficient or that stars formed in ways we didn't fully understand. One possibility is that early stars were extremely massive and short-lived, producing heavy elements faster than expected. Another is that dark matter helped seed structure more efficiently, providing gravitational scaffolding that allowed gas to collapse rapidly. Webb doesn't yet give a final answer, but it narrows the range of viable explanations. Webb has also transformed our understanding of the so-called cosmic dawn, the era when the first stars lit up the universe. This period ended the cosmic dark ages, when the universe was filled mostly with neutral hydrogen that absorbed light. As stars formed, their radiation ionized this hydrogen, making space transparent. This process is known as rayonization. Before Webb, rayonization was studied indirectly. Astronomers inferred its timing by looking at the absorption patterns in distant quasars. Webb now observes galaxies directly from this era, allowing scientists to see which sources likely drove rayonization. What Webb shows is that early galaxies were not uniformly small and dim. Some were surprisingly luminous, capable of producing enough radiation to affect their surroundings. This means rayonization may have happened faster and more unevenly than once thought, driven by clusters of energetic galaxies rather than a slow, uniform glow. Another striking discovery involves galaxy shapes. Early galaxies were expected to be chaotic and irregular, shaped by frequent mergers. While many are, Webb also finds disk-like structures surprisingly early. Disk galaxies, like the Milky Way, were thought to require long periods of calm evolution. Finding early disks suggests that some regions of the universe were stable sooner than expected. This challenges the idea that the early universe was universally violent. Instead, Webb paints a picture of diversity. Some regions were turbulent, while others settled quickly into orderly patterns. Webb also reveals that supermassive black holes appeared very early. These black holes, millions or even billions of times the mass of the Sun, were once thought to grow slowly from smaller seeds. Webb finds them powering quasars less than a billion years after the Big Bang. This raises a fundamental question. How did they grow so fast? Possible answers include the formation of massive black hole seeds directly from collapsing gas clouds or periods of extremely rapid accretion. Either way, Webb forces theorists to rethink black hole growth models and the role black holes played in shaping early galaxies. Another major contribution of Webb is its ability to analyze the chemical composition of early galaxies. By splitting light into spectra, Webb detects elements like carbon, oxygen, and nitrogen far earlier than expected. These elements are forged in stars, meaning stellar life cycles were already well underway. This chemical maturity suggests that star formation began earlier, proceeded faster, or occurred in environments more efficient than predicted. It also implies that the building blocks of planets, and potentially life, were available surprisingly early in cosmic history. Think of it like discovering that a kitchen was stocked and cooking elaborate meals long before anyone thought the grocery store existed. Webb's discoveries don't contradict the Big Bang. Instead, they enrich it. The universe still began hot and dense, expanded, cooled, and formed structure. But the pace, efficiency, and diversity of that process now appear far more dynamic than previously imagined. Importantly, Webb is not just finding rare exceptions. The sheer number of early, massive galaxies suggests these were not cosmic flukes. They indicate a general trend that models must account for. This has led to a wave of new simulations, updated theories, and debates. Some researchers propose tweaks to dark matter behavior. Others explore changes to star formation physics or feedback processes. A few even question aspects of cosmological assumptions, though such ideas face high scrutiny. What remains clear is that Webb has moved cosmology from extrapolation to observation. Instead of guessing how the early universe behaved, scientists now have direct evidence. And this deeper view into cosmic history naturally raises another question. If galaxies, stars and black holes formed so early and so rapidly, what does that say about the raw materials of the universe itself? To answer that, we must examine what Webb reveals about the contents of the cosmos, its gas, dust, and chemical evolution. That exploration is where the story continues next. As James Webb pushes deeper into the universe's past, it also peers into something just as important, but far less visible: the material that fills the space between stars and galaxies. For decades, astronomers built their understanding of cosmic evolution mostly from what they could see directly: stars glowing in visible light. But stars are only part of the story. The real architecture of the universe is shaped by gas, dust, radiation, and gravity, working together in ways that were often hidden from earlier telescopes. This is where Webb's infrared vision becomes transformative. Gas is the raw fuel of the universe. Stars form when clouds of gas collapse under gravity, and galaxies grow by gathering vast reservoirs of it. Yet much of this gas is cold and invisible to optical telescopes. Dust, made of tiny grains of carbon and silicates, further obscures these regions by blocking visible light. Before Webb, astronomers knew this material existed, but much of it was inferred rather than observed directly. Webb doesn't just infer, it sees. By observing in infrared wavelengths, Webb can look through dust the way fog lights cut through mist. Regions that once appeared dark and empty now reveal intricate structures: dense knots of gas, filamentary networks, and glowing pockets where stars are being born. This has dramatically changed how scientists understand where and how stars form. One surprising result is just how organized many of these regions are. Star-forming clouds were often imagined as chaotic blobs, stirred by turbulence and explosions from nearby stars. Webb shows that while turbulence exists, gravity often sculpts gas into long, coherent filaments that act like cosmic highways, channeling material toward growing stars. A useful analogy is rainwater flowing down hills into rivers. The water doesn't fall randomly. It follows paths shaped by the landscape. Similarly, gas in galaxies follows gravitational contours shaped by dark matter and existing stars. Webb lets us see these paths for the first time in exquisite detail. Dust, once considered a nuisance because it blocks light, turns out to be a storyteller. Webb can analyze how dust absorbs and re-emits radiation, revealing its composition and temperature. Different dust grains form in different environments, some in dying stars, others in supernova explosions. By mapping dust properties, Webb reconstructs the life cycles of stars and the chemical history of galaxies. One of the most important discoveries is that dust appears surprisingly early in the universe. Webb finds significant amounts of dust in galaxies only a few 100 million years after the Big Bang. This was unexpected because dust requires heavy elements, which are produced in stars. The presence of dust so early implies that stars lived, died, and enriched their surroundings at an astonishing pace. This discovery affects more than galaxy evolution. Dust plays a crucial role in planet formation. It clumps together, forming the seeds of planets around young stars. If dust existed early, the basic ingredients for planetary systems may have been present far earlier than once assumed. Webb also allows astronomers to study molecular gas directly. Molecules like hydrogen, carbon monoxide, and water emit specific infrared signatures. By detecting these signals, Webb measures how much star-forming material galaxies contain and how efficiently they turn gas into stars. What it finds is variety. Some galaxies are star factories, converting gas into stars at breakneck speed. Others hold large gas reserves, but form stars slowly, as if restrained by internal processes or environmental factors. This diversity suggests that galaxy growth is not governed by a single universal rule, but by a balance of competing influences. Radiation from young stars can heat gas and slow further collapse. Supernova explosions can blow gas out of galaxies entirely. Black holes can inject enormous energy into their surroundings, regulating growth on galactic scales. Webb observes these feedback processes in action, revealing how galaxies self-regulate over time. Another key insight involves the intergalactic medium, the vast space between galaxies filled with thin gas. This medium acts like a cosmic reservoir, supplying galaxies with fresh material. Webb detects faint infrared signals from this gas, helping astronomers understand how matter flows across the universe's large-scale structure. Think of galaxies as cities, and the intergalactic medium as the countryside supplying food and resources. Without constant inflow, cities stagnate. Webb shows that galaxies are deeply connected to their environments, fed by invisible streams of gas stretching across millions of light years. Webb's chemical measurements also refine our understanding of cosmic evolution. By tracking how elements like oxygen, carbon, and nitrogen increase over time, scientists can test models of stellar life cycles and galaxy growth. These observations confirm that the universe becomes chemically richer over time, but they also reveal surprising early enrichment. This early chemical complexity suggests that the universe was primed for structure from the beginning. The basic building blocks didn't slowly trickle into existence. They appeared rapidly and in abundance. All of this reshapes how scientists think about the universe's contents. The cosmos is not mostly empty space punctuated by stars. It is a dynamic, interconnected system filled with material in different states, constantly cycling between gas, stars, dust, and radiation. James Webb doesn't just show us new objects, it shows us the processes that connect them. And once you understand how matter moves and evolves across the universe, a deeper question naturally emerges. If we now see more structure, more material, and more complexity than ever before, what does that say about the universe's overall shape and scale? How does all of this fit into the grand cosmic architecture? That question leads directly into what Webb is revealing about the large-scale structure of the universe, and how our place within it may be different from what we once imagined. Once, astronomers began to see how gas, dust, and stars flow together inside galaxies. A much larger question moved into focus. If matter is organized on small scales by gravity and feedback, what does that organization look like when stretched across the entire universe? This is where James Webb has begun to reshape our understanding of cosmic structure itself. For a long time, astronomers described the universe on its largest scales using an evocative metaphor: the cosmic web. Galaxies are not scattered randomly through space. Instead, they trace enormous filaments of matter, stretching across hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form. Between these filaments lie vast voids, regions with very few galaxies at all. Before Webb, much of this structure was mapped indirectly. Astronomers used visible light surveys and computer simulations to infer how matter should be distributed, especially the invisible dark matter that dominates cosmic mass. Webb now allows researchers to test those models against reality with unprecedented clarity. By observing distant galaxies at different epochs, Webb effectively lets astronomers watch the cosmic web assembling over time. In the early universe, matter was more evenly spread. Tiny density differences, seeded shortly after the Big Bang, slowly grew under gravity. Over billions of years, these small ripples amplified into the enormous filaments we see today. A helpful analogy is bread dough rising. At first, the dough looks smooth. As it expands, tiny air bubbles form, grow, and connect, creating a complex internal structure. The universe behaves similarly, except gravity replaces yeast, and dark matter provides the scaffolding. Webb's observations show that filamentary structure appears earlier than expected. Galaxies at extreme distances already show alignment along preferred directions, hinting that large-scale organization began sooner and developed faster than many simulations predicted. This matters because the speed and pattern of structure formation depend on fundamental properties of the universe: the amount of dark matter, the behavior of dark energy, and the physics governing cosmic expansion. If structure formed earlier, it may suggest subtle adjustments to existing models. Webb also sharpens our understanding of galaxy clusters, the most massive bound objects in the universe. These clusters act like cosmic crossroads where filaments intersect. By measuring galaxy motions, gas temperatures, and gravitational lensing effects, Webb helps astronomers estimate cluster masses with greater precision. Gravitational lensing, in particular, becomes a powerful tool. Massive clusters bend space itself, magnifying background galaxies like natural telescopes. Webb uses this effect to peer even deeper into the universe, while simultaneously mapping the cluster's invisible dark matter distribution. It's a bit like seeing a distorted reflection in a funhouse mirror, and using that distortion to infer the mirror's shape. The way background galaxies stretch and warp tells scientists exactly how mass is distributed in the foreground cluster. One striking result is that dark matter appears remarkably smooth on large scales, but clumpy on smaller ones, just as simulations predicted. This strengthens the case for dark matter as a fundamental cosmic ingredient rather than a mathematical placeholder. At the same time, Webb reveals subtle tensions. Some observed structures appear slightly more compact or more evolved than expected for their age. These discrepancies are small, but they matter, because cosmology is now a precision science. Even a few % difference can point toward new physics. Another major contribution comes from Webb's ability to study the environments around supermassive black holes. These objects are not isolated curiosities. They influence their surroundings on vast scales. Webb shows how black holes inject energy into their host galaxies and even into surrounding intergalactic gas. This feedback can slow star formation, heat gas, and alter how matter flows along cosmic filaments. In effect, black holes help shape the large-scale structure of the universe, not just their immediate neighborhoods. If galaxies are cities, black holes are industrial centers that regulate growth, sometimes boosting activity, sometimes shutting it down. Webb's data suggest that this regulation began earlier and was more widespread than previously believed. As all of these observations accumulate, a clearer picture emerges. The universe is not simply expanding space filled with isolated galaxies. It is a connected system where matter, energy, and geometry interact across immense distances. This brings us to one of Webb's most profound impacts, refining how we measure the universe itself. Distances in cosmology are notoriously difficult. Astronomers rely on a ladder of measurements, from nearby stars to distant galaxies, each rung calibrated by the one below. Webb strengthens this ladder by providing more accurate measurements of stellar populations, galaxy brightness, and redshifts. In some cases, Webb confirms earlier results. In others, it exposes inconsistencies that force scientists to re-examine assumptions. One such issue is the ongoing tension between different measurements of the universe's expansion rate. Webb does not resolve this tension outright, but it narrows the uncertainty. It shows that discrepancies are not simply due to measurement errors, suggesting that new physics may be involved. This is where the story shifts from mapping structure to questioning the underlying rules of the cosmos. If the universe is larger, more structured, and more complex than we thought, are our foundational theories complete? That question naturally leads into the next phase of Webb's legacy: how its discoveries challenge our understanding of cosmic history, including the timeline of galaxy formation, black hole growth, and the evolution of space itself. And that is where the next part of the story begins. As astronomers dig deeper into the structure of the universe, they inevitably turn their attention to its history. Not just when things formed, but how fast they formed, and whether the timeline we once trusted still holds up under closer inspection. This is where James Webb has been quietly disruptive. For decades, cosmologists relied on a fairly clean narrative of cosmic history. First came the Big Bang, followed by a brief period of rapid expansion. Then the universe cooled, particles formed, atoms assembled, and after a long dark age, the first stars ignited. Galaxies slowly grew, merged, and evolved into the diverse population we see today. Webb hasn't overturned this story, but it has complicated it in important ways. One of the telescope's most surprising contributions is how early it sees mature structures. Galaxies that appear only a few 100 million years after the Big Bang already show organized disks, heavy elements, and signs of sustained star formation. According to older models, these features should have taken much longer to develop. To understand why this matters, imagine discovering a fully developed city, complete with highways, neighborhoods, and infrastructure, just a few years after the first humans learned how to build huts. You wouldn't conclude that cities are impossible. You'd conclude that your assumptions about how quickly construction can happen are incomplete. Webb is forcing a similar reckoning in cosmology. Heavy elements like carbon, oxygen, and iron are forged inside stars and spread through space when those stars die. Finding these elements in very young galaxies means that massive stars must have formed, lived, and exploded extremely quickly. This suggests that early star formation was more intense and efficient than previously thought. In practical terms, the early universe may have been far more productive than we imagined. Instead of a slow, gradual awakening, it may have experienced rapid bursts of activity. lighting up space with stars and black holes sooner than expected. This has direct implications for how Ryanization unfolded. Ryanization refers to the period when the first stars and galaxies emitted enough energetic light to strip electrons from hydrogen atoms, transforming the universe from opaque to transparent. Webb's observations suggest that galaxies alone may have been capable of driving this process earlier and more decisively than models once assumed. Another piece of this puzzle comes from Webb's observations of early black holes. Supermassive black holes appear surprisingly massive at very early times, raising a difficult question. How did they grow so big so fast? Black holes grow by consuming matter, but there are physical limits on how quickly they can accrete without blowing away their own fuel. Webb's data hint that some black holes may have formed from unusually massive initial seeds, or that early conditions allowed for rapid, sustained growth. A useful analogy is starting a fire. You can either begin with a spark and slowly add fuel, or you can start with a large, burning log. Webb suggests the universe may have chosen the second option more often than we thought. These early black holes were not just passive objects. Their energetic output influenced surrounding gas, regulating star formation and shaping early galaxies. In effect, black holes were active participants in cosmic evolution from very early times. Webb also provides new insight into galaxy mergers. The early universe was smaller and denser, making interactions more common. Webb shows that many early galaxies grew not just by forming stars internally, but by repeatedly merging with others. This constant reshaping produced galaxies that evolved quickly and irregularly, challenging the idea of a smooth, orderly buildup. Cosmic history appears less like a slow construction project and more like a bustling marketplace, full of collisions, exchanges, and rapid transformations. At the same time, Webb's precision reveals continuity amid the chaos. Despite the faster pace, the same physical laws appear to govern star formation, gravity, and radiation across cosmic time. The universe follows consistent rules, even when operating under extreme conditions. This balance between familiarity and surprise is one of Webb's greatest strengths. It doesn't replace existing theories wholesale. Instead, it refines them, nudges them, and occasionally exposes cracks that demand attention. Another important contribution comes from Webb's ability to study cosmic dust. Dust may seem insignificant, but it plays a crucial role in cooling gas and enabling star formation. Webb shows that dust appeared earlier than expected, suggesting rapid enrichment of the interstellar medium. This early dust affects how light travels, how stars form, and how galaxies evolve. It also complicates observations, since dust can obscure and redden light. Webb's infrared vision allows astronomers to see through this veil, revealing a more complete picture of early cosmic environments. As a result, timelines based solely on visible light observations are being recalibrated. Some galaxies once thought to be primitive now appear more advanced, simply hidden behind dust. All of this feeds into a broader realization. The universe's early chapters are more dynamic, more crowded, and more efficient than we assumed. And if the early universe behaved differently, that affects everything downstream. The sizes of galaxies, the distribution of matter, the growth of structure, and even measurements of cosmic expansion all depend on initial conditions. Webb's findings don't just fill in missing details. They reshape the context in which all later cosmic evolution unfolds. Which naturally leads to a deeper question. If the universe formed structures faster, grew more complex earlier, and organized itself on vast scales sooner than expected, what does that say about the fundamental forces driving its expansion? That question draws us toward the relationship between matter, energy, and the accelerating universe itself, and how Webb is helping us probe the most mysterious component of all, dark energy. And that is where the story continues next. When astronomers talk about the size of the universe, they are not just talking about how far light has traveled. They are talking about how space itself behaves, how it stretches, and how that stretching changes the meaning of distance over time. This is where James Webb has begun to influence one of the most important and unsettled debates in modern cosmology. For nearly a century, scientists have known that the universe is expanding. Galaxies are moving away from one another, not because they were launched outward like shrapnel, but because the space between them is growing. A useful analogy is dots drawn on a balloon. As the balloon inflates, every dot moves away from every other dot, even though none of the dots are actively crawling across the surface. This expansion sets the scale of the universe. It determines how old it is, how large it has become, and how fast it is changing today. The rate of this expansion is described by a number called the Hubble constant. For years, astronomers believed they were closing in on a precise value. Then something strange happened. Different methods began producing different answers. Measurements based on nearby galaxies and supernovae suggested the universe is expanding faster today. Measurements based on the early universe using the cosmic microwave background suggested a slower rate. This disagreement is known as the Hubble tension, and it is not a small discrepancy. It is large enough that it cannot easily be explained away by measurement error. James Webb entered this debate quietly but decisively. One of Webb's strengths is its ability to measure distances with extraordinary precision. It can observe Cepheid, variable stars, and supernovae in dusty environments that were previously difficult to study. These objects act like cosmic yardsticks, allowing astronomers to calculate distances step by step across the universe. By refining these measurements, Webb has confirmed that the local universe really does appear to be expanding faster than early universe models predict. This strengthens the tension rather than resolving it. To understand why this matters, imagine timing a race using two perfectly calibrated clocks placed at different points along the track. If one clock insists the runner is faster than the other, something fundamental about your assumptions must be wrong. Either the clocks operate differently, or the track itself is changing. In cosmology, that track is space-time. One possible explanation is that dark energy, the mysterious force driving cosmic acceleration, is not constant. Instead of behaving like a steady pressure, it may evolve over time. Webb's observations of distant galaxies help test this idea by revealing how structures formed at different epochs under different expansion conditions. So far, Webb's data suggest that dark energy behaves remarkably smoothly, but subtle deviations remain possible. Even small changes in dark energy's behavior could reshape the universe's long-term fate. Another possibility is that our models of the early universe are incomplete. The cosmic microwave background provides a snapshot of the universe when it was only about 380,000 years old. If unknown physics influenced conditions before or during that time, it could skew our interpretation of later expansion. Webb contributes here by observing galaxies so distant that their light has traveled for more than 13 billion years. These galaxies act as time capsules, offering a direct view of cosmic conditions close to the universe's beginning. What Webb sees suggests a universe that was structured, energetic, and complex surprisingly early. This pushes against models that assume slower, simpler beginnings. There is also the possibility that gravity itself behaves differently on the largest scales. General relativity has passed every test so far, but it has never been tested directly across the full span of cosmic distances. Webb's observations of galaxy clustering, lensing, and large-scale structure help probe whether gravity remains unchanged across billions of light-years. The scale of the universe, then, is not just about size. It is about consistency. It is about whether the same rules apply everywhere, at every time. Webb's data increasingly suggest that the universe is both larger and more intricate than we once imagined. Galaxies are forming earlier, structures are growing faster, and cosmic distances may be stretching in subtly unexpected ways. This does not mean the universe is unstable or unpredictable. Rather, it suggests that our previous measurements were limited by perspective. Webb is offering a wider lens, revealing details that were always there but previously hidden. There's also a psychological aspect to this shift. Humans are comfortable with static maps. We like knowing where things are and how far away they sit. But the universe does not provide a fixed map. Its ruler stretches as you measure with it. A light year is not a frozen unit. A galaxy that was once 10 billion light-years away may now be much farther due to expansion. Webb's observations force us to think in terms of evolving distances rather than static separations. This realization alters how we think about the universe's true scale. The observable universe has a radius of about 46 billion light-years, even though the universe is only 13.8 billion years old. That apparent contradiction exists because space expanded while light was traveling. Webb's ability to study the earliest galaxies sharpens this picture. It shows us not just where the universe is now, but how fast it grew and how its growth rate may be changing. As a result, cosmology is entering a phase where precision matters more than ever. Small discrepancies can point to major discoveries. Webb is not delivering dramatic overturns of theory, but it is steadily tightening constraints, narrowing possibilities, and exposing the edges of our understanding. And those edges matter, because when we ask how big the universe is, we are also asking whether it has limits, whether its laws are uniform, and whether its future is already written or still unfolding. James Webb has not answered those questions outright, but it has transformed them from abstract speculation into testable science. And that transformation leads naturally to one final consideration: what all of this means for the future of cosmology, for humanity's place in the universe, and for the questions that may remain permanently beyond our reach. That is where the story concludes next. At this point, it becomes clear that the James Webb Space Telescope has not simply added new details to our picture of the universe. It has changed the way we think about discovery itself. Instead of answering one grand question and moving on, Webb has revealed that the universe is layered with questions that unfold the deeper we look. One of the most important realizations to emerge from Webb's observations is that there may never be a single moment when we can say, "Now we know the universe completely." The cosmos is not a puzzle with a final piece waiting to be snapped into place. It is more like a landscape that expands as we walk through it. Each new vantage point reveals more terrain, not a boundary. This does not mean science is failing. In fact, it means science is doing exactly what it is meant to do. James Webb has demonstrated that the universe is larger, older, and more structurally complex than earlier instruments could reveal. It has shown us galaxies forming earlier than expected, black holes growing faster than models predicted, and chemical complexity emerging sooner than theories once allowed. None of these discoveries invalidate previous science. They refine it. A useful analogy is updating a map. Early explorers drew coastlines based on what they could see from ships. Later explorers filled in rivers, mountains, and cities. The early maps were not wrong. They were incomplete. Webb represents a new generation of mapping tools, allowing us to see the cosmic interior, not just the outline. Another critical lesson from Webb is that observation shapes understanding. The universe did not change when Webb launched. Our access to it did. Infrared vision allows us to see through dust, to detect cooler objects, and to capture light stretched by billions of years of expansion. Entire populations of galaxies were always there. We simply lacked the eyes to see them. This realization humbles our confidence in final answers. It reminds us that future instruments may reveal aspects of the universe that Webb itself cannot detect. Dark matter may remain invisible. Dark energy may resist direct measurement. Some regions of the universe may forever lie beyond our observational horizon. And that is okay. There's a quiet strength in accepting limits without surrendering curiosity. Webb has shown that even within those limits, there's extraordinary richness to uncover. The universe is not withholding truth out of hostility. It is operating according to laws that do not prioritize human convenience. In practical terms, Webb's discoveries will guide cosmology for decades. They will refine simulations of galaxy formation, constrain models of cosmic inflation, sharpen measurements of expansion, and influence the design of future telescopes. Missions now being planned already assume a universe that is more dynamic and complex than the one described in textbooks just a decade ago. There is also a broader human impact. Webb reminds us that progress does not always come from radical revolutions. Sometimes it comes from better listening, better instruments, better patience. By collecting clearer data, Webb allows nature to speak more precisely. Perhaps most importantly, Webb reframes humanity's relationship with scale. The universe is vast beyond intuition, but not indifferent to understanding. Physical laws remain consistent across billions of light years. Patterns repeat. Structure emerges. Complexity builds upon simplicity. That consistency is what allows science to work at all. When we ask how big the universe truly is, we are also asking how much of it is knowable. Webb suggests that while the universe may be effectively limitless, our ability to understand it is not meaningless or trivial. Each improvement in observation expands our conceptual reach, even if the horizon recedes. In this sense, the universe is not mocking our curiosity. It is responding to it, slowly, incrementally but honestly. James Webb has not delivered a final answer about the universe's true scale. Instead, it has delivered something far more valuable: clarity about where our understanding stands, where it is strong, and where it remains incomplete. That clarity is the foundation of real progress, and so the story does not end with a conclusion, but with continuity. The universe remains open, evolving, and accessible to inquiry. The tools improve, the questions sharpen, the picture grows richer. James Webb has not shown us everything, but it has shown us enough to know that the universe is far more than we once imagined, and that understanding it will remain one of humanity's most enduring and rewarding pursuits.